Hello, everybody. Welcome to Monday's thermodynamics lecture. Today I'm going to be talking some more about the second law and finishing up the chapter 5, and hopefully we can move on to chapter 6 today and talk a little bit about entropy, which is sort of the thing we've been meaning to talk about now for a little while and sort of dancing around the subject. I feel like it's about time that we just get right into entropy and go right after it. So today I'm going to talk a little bit about that. Let me see if I can get the right slide up here. Okay, so as usual on the beginning of our lectures, we consult the previous survey question that we had, and so let's see how people did here. Okay, not as good as previous surveys, but let's take a look here. According to the Clausius inequality, the value of sigma cannot be positive. No, it can be positive because it's negative, right? So so a negative sigma means that the cycle is impossible. A positive sigma means that the cycle is irreversible. Zero sigma, one of you said that, but that means the cycle is irreversible, and or a process is irreversible. And this is my nonsensical answer. So let's see, greater than the net work output. Well, I mean, yeah, technically the value of sigma is not equal to the is not greater than the net work output. I mean, just because they have nothing to do with each other. As we remember, only the temperature is in the Clausius inequality. As you remember, let's go back and look and see what we did here. So if we look at the second law, we're going to do this example next. Let's look at it here. So here we go. This is it. Nothing to do with work in here. There's no work. It says here that the cyclic integral for some process that goes around in a cycle, or for any process for that matter, the change in energy over the temperature at which that change in heat over which the temperature at which that heat transfer happens is equal to negative sigma of the cycle. Okay, so where the sigma can be zero, because it means that there's no irreversibility since it's in a totally reversible process. Sigma of the cycle is greater than zero, means irreversibilities are present within the system. Or sigma is less than zero, means it's impossible. Okay, so all you really had to do for this survey is to look at this slide and you would have the answer. Okay, so what this means to me is that some of you are trying to do the survey without looking at my lecture or even opening my slides. So please do that. I understand that it's difficult times and things are tricky, but I really appreciate it if you would just take a look at those things and please keep up with the material if you can. Okay. All right. So let's see. What are we doing next? So next thing we're going to do here is we are going to do a final second law example before we move on. And the final example he is given here, it's actually a little complex. It's a cycle. Okay. So it's a thermodynamic cycle that we're going to solve. To solve this cycle, what we're going to do, let me get to the right screen here. Okay, so here we go. Here's the cycle. The figure gives a schematic of a vapor power plant in which the water steadily circulates through four components. Okay, the four components, so let's see, the four components are a pump, boiler, turbine, condenser. The water flows through the boiler and condenser at constant pressure and through a turbine and pump adiabatically. Ignore potential kinetic and potential energy effects. And the process data are as follows. So process 4-1 is a constant pressure process at 1 megapascals, operating from saturated liquid to saturated vapor. And then 2-3 actually operates within the vapor dome, it looks like. Constant pressure at 20 kilopascals from X2 equals 88% to X3, which is the quality at 18%. So it's dropping quality. Determine if the cycle is internally reversible, or impossible. Okay? Mission impossible. Determine if the thermal efficiency expressed on a time rate basis in using the steam table. Okay, steam table data. All right, so let's do that. Let's see. So let's see. What we have here is, so I'm just going to say, I'm going to start the process here. Then we have a cycle with given processes. What we're supposed to find is whether cycle is reversible, etc. Okay, and also determine the thermal efficiency. Thermal efficiency expressed in time rate based on steam. Whoa, we got the cat again. Hello, this is Lola, by the way. She likes to jump up on my screen when I'm giving lectures. She can sit here on my lap, actually. If she behaves, she can sit on my lap. And the thermal efficiency, okay? And so let's try to figure this out here. All right, Lola, you ready? Okay, let's do this. All right, so next thing we're gonna do here is we gotta do some assumptions. Okay, so the assumptions are that we have a, let's see, we'll have a, so we have a steady state. First thing is we're going to assume we have a steady state cycle. We have a steady state cycle. 2, let's see, we're going to say that, yeah, we have heat and energy, or heat and work. Work in directions shown on the diagram, but we're gonna, well, maybe we'll remake the diagram. Essentially our system is here, right? So that we have some work and heat kind of crossing the boundary, going in and out. So we're assuming this is Q in and Q out. Okay, anything else we do? Let's see, we're gonna neglect kinetic energy and potential energy differences. Anything else? I guess we're going to assume that we have some adiabatic processes, but all right, so we have some processes that are adiabatic. Big deal. Okay, we'll get into that when we talk about the individual processes. Okay, so let's first make a diagram of what happens in the cycle. Okay, so the one diagram we really need to make. What diagram we really need to make is a diagram, what's called the well, of course, let's just make a PV diagram, right? So we have P and V here. So remember that whenever you have a cycle that operates with saturated liquid and saturated vapor, you've got to put it under the vapor dome. Okay, the vapor dome. Remember, the vapor dome looks like this. Okay. Oh, my vapor dome's a little lumpy. It kind of looks like more like that. Okay. Oh, that's a much better one. Okay. What do you think, Lola? Is that good? Okay. Okay, now let's see. Process. Well, what processes are we talking about first here? Process 4-1 is a constant pressure at 1 megapascal, so it's at higher pressure. So process 4-1 here is boiler, right? So boiler is happening at constant pressure and there's heat going in. And it operates from the saturated, from saturated liquid to saturated vapor at 1 megapascal. Okay, so you know it operates from here, from 4 to 1. Like that, okay? Remember that. Okay, so the first thing is, it's a constant pressure process, and it's going across the vapor dome at 1 megapascals. Okay, so then we could just make these things like this, right? This is at 1 megapascal. Actually, that's temperature. Sorry, this is 1 megapascal. Okay, we just say MPa here. Okay, we can do that. And then we have process 2 to 3, which is the other constant pressure process at 20 kilopascals from X2 to X3, which is 88 to 18. All right, so it's going to be kind of like, oops, put the eraser on. Here we go. Here, and, whoops, let's see. So let's draw this constant pressure, the constant temperature line like this, okay? And this is the, let's see, let's get rid of this here. So this is 2, and this is 3, and so it's like this. So we're gonna 1, 2, 3, 4. Okay, so these are, well, let's see, water through the boiling condenser and through the pump and adiabatic. So these are adiabatic. So 1 to 2, as you see up here, 1 to 2 is a turbine. We're making work. And so we're just going to say we have some work here. 4 to 1, we have some heat in. So sometimes we do this in these cycles. So we have Q in, we have Q out. We know right away that this cycle is possible, right? We're not exchanging heat with only one reservoir. We're making work, but we're not, we have some work going in here. So this is an interesting cycle, actually, since we're operating all inside the vapor dome. This would never work. This pump would never work, actually. From process 3 to 4, forget it. You can never pump stuff that's like all bubbly, saturated liquid stuff. That would never work, okay? So no matter whether this is a thermodynamically possible cycle, it's an actual like impossible physical cycle. Usually we do the pump. When we do the Rankine cycle, we'll tell you all about this. But for now, okay, this is our process. 1, 2, 3. So we have 1, 2, 3, and 4. Okay. All right. I think we're good now. So we have work in, we have work out. I think that's what they're calling it here. Work turbine, work pump. I'm going to call it work in and work out. Okay. All right. So now, let's do analysis here. So what we're really trying to find is we need to find the sigma to determine whether the cycle is irreversible or impossible or reversible. So we're going to use this one. And remember, as I said, has nothing to do with the work. Who cares about the work? Okay, this is all about the Q. So Q dot 23 over the temperature at which that happens, T23. In this case, T23 is constant. Oh, phew, no integration necessary. Okay, and then minus. Let's see, we have minus the Q401 over T401. Okay, so now how are we going to solve this? So Q41, let's do the first law. So Q41 equals m dot H1 minus H4. Is that right? Yeah, because essentially we have no work, right? So no work term plus work term, we're going to just call it 0. Right, so this is, and we call this Q dot in, right? Right, and remember that, okay, so this is example 1 continued. So then remember that what we have to do is look at the vapor tape. So we look at the PV diagram. So this is actually a little easy to look it up, right? Because if we have 1 megapascal, so this Q in is equal to m dot times HFG, which is HF minus HG at 1 megapascal, right? And then that's pretty simple to find. We're going to just have to find this later. But if we want to do Q23, we're going to need to find that. So Q23 is also equal to the same thing, m dot H2 minus H3. But in this case, we have to use the steam quality, right? So this is going to be m dot. Remember that m dot is constant because the cycle is at steady state and the fluid is going all the way around it. Okay, so there's no the cycle is constant. So then m dot times HF plus X HFG evaluated at state 2. Oops, I'm going to run out of room. HF plus X HFG evaluated at 3 at state 3. So these are at the same pressure, so this is actually not so bad. So this is not so bad, right? Yeah, X HFG. So we can just simplify it maybe m dot because they're at the constant pressure. We can just say this is X2 minus X3 HFG at this is HFG at 20 kilopascals. Okay. All right. So let's do this. So yeah. All right, good. So this is pretty good. So HF, remember HFG is equal to HF minus HG at some pressure. Okay, remember that. Okay, just wanted to make that clear. Don't get confused by that. Okay. All right. So let's see. So then let's just plug that into our. Oops, that's not what I want. Into our sigma of the cycle equation is equal to x2 minus x3 HFG at 20 kilopascals over T3 T23, which is Tsat, the saturated temperature at 20 kilopascals. So this is Tsat at 20 kPa. And then we can look up these things at the pressure table. This is HFG of 1 megapascal over T41. So, which is Tsat at 1 megapascal. Okay? All right. So if we look at the saturated pressure table, which is from table A3, I'm not going to look at the table, okay? I'm assuming you guys, I'm not going to show you what the table looks like. I think you guys are good enough by now to figure out where the table is. I have the numbers copied down here, so I'm going to just use the numbers. And the cat is shedding all over me, so this is springtime. Springtime with kitties. Okay, here we go. Yeah. Okay, she's still here. Okay. You like thermodynamics, huh? Okay, or you're hungry. Either one or the other. Okay, so let's go. Let's see, T41. So let's see. Tsat T41, which is Tsat at the higher pressure, is 179.9 degrees C, and HFG at that pressure is equal to 2015.3 kilojoules per kilogram. Make sure I get my numbers. You can read them. So, and T23 is equal to, at the lower pressure, is equal to 60.1 degrees C. And then you have HFG, this is 40123, is equal to 2358.3 kilojoules per kilogram. Okay. And then so if we plug all these things in and we just go, so we're not given m dot, but we can just divide by m dot. No big deal, because m dot's constant and it doesn't really change the direction of the sign because it's being multiplied by the whole thing. So it's not a big deal, right? We can just, in fact, I think I should have done that already up here, right? Because I got rid of m dot already. Okay, so so if we do all this and plug all the numbers in, we get 0.88 minus 0.18, which are the qualities, times 23, oops. Let's see, 2358. I'm just going to leave the decimal places off because it's not going to make very much difference. What is it? Make sure it's in K, 333.2. And this is in K, because you have to have it in K, right? For because we're talking about the Kelvin scale. Remember the Kelvin temperature scale? Always use Kelvin, okay? Even though the steam tables are given in C, don't make the mistake of dividing by things in degrees C, okay? All right, so, okay, then we're going to use 2015 here, and we're going to go for 53K here, 453.1K here, is equal to 0.51 kilojoules per kilogram K. All right, great. So this is our answer. Okay, which essentially means that we have an irreversible cycle because sigma is positive. If sigma were negative, it would be impossible. If sigma were 0, it would be irreversible. So it's irreversible. There's two R's. Irreversible cycle, okay? So this is example 1, continued again. And then we're going to do part B now. So part B is asking for the thermal efficiency of this cycle. So Just think back. What do you remember about thermal efficiency? What is it? Okay. No, it's not that. Yeah, no, that's not it. It's not it. Okay. So thermal efficiency is work of the cycle divided by heat in. Okay. Um, so we'll call this that we are calling this WN. So this is net. So this is the net work of the cycle. So net work of the cycle is the work out minus the work in, right? Presuming we have net work out, which we're just going to presume in this case. So Q dot. Oh, make sure these are dots. This is if we just do the first law, because we already know how to do the first law for a cycle, it reduces to this, right? Because you can say the work is equal to the net work out minus work in is equal to heat in minus heat out. Okay, and then you can just get this following equation, and then we already know what those are because we just solved them. 1 minus Q 2 3 over Q 4 1, and then dot dot. And then of course we don't have the dots, but we can always just divide by mass flow and we can get it. So then we're going to end up getting 1 minus x2 minus x3 hfg23 over hfg41, right? And this is equal to, if we plug this all in, I'm not going to put the numbers in, 0.18 or 18%. Pretty bad. 18% thermal efficiency, that's really bad. If we had a steam power plant that had 18% thermal efficiency, yeah, we would be paying a lot for electricity. Okay, now let's think. Let's do an extra. Let's compare this to the Carnot cycle. Because remember, for Carnot cycle, the maximum thermal efficiency is equal to 1 minus T 2 3 over T 4 1, which is equal to 1 minus T L over TH. Do you remember that? The low temperature and the high temperature reservoir. If we look back here at this diagram, we can see that that you have a constant high temperature and a constant low temperature. Therefore, the heat transfer is occurring at those temperatures, and we can assume that the reservoirs, maybe if we have perfect heat transfer between the boiler flame on one side and whatever that is, so the high temperature source is the same, we end up getting something that looks like this. So so then TL over TH, though this would be 1 minus 333.2 we just said 2 over whatever the temperature that we had up here. What was it? 453. 453.1 is equal to 20.265 or 26.5%. So this actually, thinking about it, if we wanted to really be fancy about this, we would say, okay, ideally, this cycle, okay, if it were operating under a Carnot cycle, could have 26.5% thermal efficiency, maximum, okay? Then the sigma would be 0. All right, but we actually got 18%. One could come up with a metric called the second law, which is equal to the efficiency actual, we'll say thermal efficiency, the first law, actual over Carnot. Okay? And I have not calculated this yet, so we could say 0.18, what is it? 0 divided by 0.265. Let's see, do I have a calculator? I got a new phone, so I'm of course not going to be able to find the calculator very easily, but oh yeah, here we go, I got it. Let's see, 0.18 divided by 0.265, and that is equal to, we can say that the second law of thermal efficiency is 67.9%. We call this the second law efficiency. Okay, so that's not in the chapter. I'm just giving that to you as bonus extra stuff. All right, so we can actually develop a first law efficiency, which is the efficiency here, the work out or the heat in. So we'll call this like actual. So this is a first law efficiency, and we'll call this a second law efficiency. Okay, 67.9%. That means we're getting 67.9% of the ideal efficiency for this cycle. We could get a lot better than that, right? We can get closer to the ideal efficiency if we use better processes. And as I said earlier, developing a pump that operates not in the that doesn't operate over such a huge temperature difference would be ideal. But okay, from 3 to 4, pumping fluid that's in the two-phase region is never a good thing. It's okay. So chances of that actually happening in real life is poor. Okay? So that's it for chapter 5. Let's be done with chapter 5 and move on. Okay? So the next thing I want to introduce to you is the concept of entropy. The concept of entropy is, as I said, pretty enigmatic. It's derived based on the second law. People say it's a result of the second law, the property itself, entropy. All right, I may not have time to give you a full treatise on this, but you know what? We're gonna do our best and get as far as we can. Okay. All right. So in this chapter, we're going to explain the key concept related to entropy in the second law, including entropy transfer, entropy production, and the increase in entropy principle. It's very close to the sigma idea, the idea that sigma is always positive. Evaluate entropy change between two states, and analyze isentropic processes using appropriate property data. So spoiler alert, isentropic process means adiabatic, meaning no heat loss, and reversible, meaning that the process operates in a reversible way. Okay, represent heat transfer, an internally reversible process. Okay, so on an temperature area diagram. Temperature entropy diagram. The TS diagram is going to be our new TV diagram. Okay, so we were doing PV and TV diagrams. TV and PV diagrams are not really, they're kind of redundant. But if we look at the TS diagram, that actually gives us some further information. It really can give us some insight as to what's happening in the process or a cycle. We're going to analyze closed systems and control volumes, including applying entropy balances. We're going to use entropic efficiencies for turbines, pumps, compressors, and second law analysis. Kind of like what we just did, kind of like the second law efficiency, except we're going to come up with first law efficiencies for turbines and compressors that compare them to ideal processes. So it's almost like a second law efficiency, I guess. But yeah, you'll see. That's not for some lecture. So, okay. So now let's go here. Entropy change and the entropy balance is the first thing we're going to talk about. So mass and energy are all familiar, extensive properties, right? Extensive meaning they depend on mass. Mass, of course, depends on mass because it's mass. Entropy is another important extensive property. Just like mass and energy are accounted for by mass and energy balances, entropy is also accounted for by an entropy balance. Yeah, of course, I'm not telling you what entropy is. Like mass and energy, entropy can be transferred across the system boundary. So whatever it is, it can be transferred across the system boundary. Okay. Now, the entropy change and the entropy balance are developed using this Clausius inequality, the thing that we just worked on with that example with the steam going around the cycle. Okay. Where we said that the sigma for the cycle equals 0 equals a irreversible process. Sigma is greater than 0 is irreversible, and sigma is less than 0 is impossible. Okay? So consider 2 cycles. All right, 2 cycles. One going around this loop here. If you see my mouse, you probably can. Here, let's make it bigger. Make it bigger. That's better. Oops. All right, so let's make this bigger. So the first thing we're going to look at is the cycle going around here. So 1 to 2. So the cycle going from 1 to 2 and back, 1 to 2 and back, 1 to 2 and back. Internally reversible processes. Both reversible, meaning you can go back and forth. Process A to B and B to C, blah, blah, blah. Applying the Clausius equality to each one of these cycles, essentially, integrate from 2 to 1, because obviously the temperature is not constant. So maybe the heat's not constant either. I don't know. It's changing. across the cycle, the process from 1 to 2, you get essentially that the sigma for the cycle has to be 0 because it's a reversible cycle. Okay, so the sigma has to be 0, as we've said. Likewise, for the process going the other direction, B and C, so taking the route, so B to C, so B and C, we also have sigma equals 0. So where sigma 0 cycle was 0 because the two cycles are composed of internally reversible processes. All right, so the reversible, the sigmas are 0, both pass. We call that path independence. It doesn't matter what happens between 1 and 2 and back from 2 to 1. If the cycle is internally reversible, sigma is always 0. Okay, so what this means is that if we subtract these two equations, since A and B are arbitrarily internally reversible processes linking states 1 and 2, it follows that the value of the integral is independent of the particularly internally reversible process and only depends on the end states. So it only depends on 1 and 2, the state at 1 and the state at 2. This is where we develop the idea of entropy, meaning that if you had a process that operated from, say, some state to another state, you can say that and if the Clausius inequality holds that the cycle is internally reversible between those two states, you can say it doesn't matter what happens during that process, right? So that's where we develop a property, because we said from chapter 1, sorry, I'm like moving myself around. Recall from chapter 1 that a quantity is a property if and only if its change in value between two states is path independent. And we just said that the entropy, the sigma is path independent. So whatever happens doesn't matter what happens. So we conclude that the integral represents the change in some property of the system. Okay, and we call this property the entropy, and the property is evaluated by this. So for an internally reversible process, okay, note, internally reversible process, the change in some property S2 minus S1 is equal to 1 to 2 of delta QT internally reversible. Now, remember, this is the process. It's not the cycle, right? Because we said for the cycle that if we go 1 to 2 and then 2 to 1, it would be, for an internally reversible process, it would be 0, right? Sigma would be 0. But in this case, the sigma that we would calculate, like we were just calculating in the previous example, is now equal to some change in entropy from that state. So we're not talking about a cycle anymore. We're talking about a process going from one state to another. So now we have an internally reversible process from 2 to 1. So the internally reversible process means that they develop some sort of change in entropy, some sigma, which is equal to some change in entropy. I hope that makes sense. I really hope it makes sense. Okay, so now we've defined this entropy. What do we do with it, right? So it allows the change in entropy. So the change in entropy allows the change in entropy between two states to be determined by thinking of an internally reversible process between the two states. But since entropy is a property, the value of the entropy applies to any process. As I said, any process between the two states, internally reversible or not, because it's just a state. It's just a property of that state. Okay, so it doesn't matter. Now, entropy change is introduced by the integral in the entropy change equation for which no accompanying physical picture is given. Still, the aim of our chapter is to demonstrate that entropy not only has physical significance, but also that it's pretty cool and you can use it for lots of cool stuff. Okay? All right. I think that probably thoroughly confused everybody. But I think if we start using it, you're going to just get used to it. Okay? Remember this equation. S2 minus S1 equals the integral from 2 to 1 of dq over some temperature at which that heat transfer occurs for an internally reversible process. Okay? All right. Now, your little facts. So entropy is an extensive property. Like any other extensive property, the change in entropy can be positive, negative, or 0. So unlike the sigma, which could only be negative, or I'm sorry, which could only be positive or 0, the entropy can change, right? It doesn't matter. It's just for a process. It's not for a cycle or anything. It says S2 minus S1 is greater than 0, equal to 0, or less than 0. So we can look at the entropy as, the other thing. The other thing we can do is we can look and see what the units might look like. And since it's Q over T, we know it's kilojoules per kilogram K, right? And so kilojoules per, well, okay. So big S is kilojoules per K. Okay, and little s would be kilojoules per kilogram K, specific entropy, right? Which is the next line here. Okay, now, so for problem solving, the values of specific entropy are provided in A2 through A18, and specific values for entropy are obtained from these tables using the same procedures as specific volume, internal energy, and enthalpy. Okay, so we can find them the same way in the tables. Remember, if you've been looking at the tables, you notice that there's an S column. And so you knew at some point we were going to start using it, right? So now is the time we're starting to use it. All right, so now we have S equals, so of course the quality equation still occurs because S is constant across the vapor dome as well, as we'll find out. And for two-phase mixtures, of course, at the for liquid water, you can assume the same thing we assume for enthalpy and for a specific volume, that the little s at some temperature and pressure is equal to the SF, so the fluid state at that temperature, and not function of pressure. Okay. All right, so we can use the same equations that we had used before. We just actually used that equation to use for the enthalpy, and now we're going to use it for entropy. Okay, this leads us to the next and last thing that I'm going to talk about today, and that is this TS diagram, which I just mentioned, which is the diagram on the left. You see it? It has the same shape as the PV diagram we just made. In fact, but this one's nice. I can actually make it look almost symmetrical. It looks almost symmetrical. The PV diagram kind of looked like a slope. What we have in here is a temperature, but remember that temperature and pressure are constant across the diagram. So if you only have, as long as we have temperature on the y-axis, pressure remains constant, and so you get these constant pressure lines for the TS diagram. And you see that the temperature is the critical point here is the top where you go to supercritical. But then now you have S on the x-axis, and you see lines of different quality here. So you have quality of 20% and quality of 90% here. You have the saturated vapor, saturated liquid, just like we've been talking about, except now we have it on a TS diagram. From now on, when we do sort of steam stuff, I'm going to be using the TS diagram probably more often than the other two. It's easier to draw and stuff. The other diagram we could make is called the molar diagram, which is the entropy diagram. And this one looks the following. It's a little wonkier to look at. I don't know. It's not as easy to look at for me. I find it a little not as useful. I like PV and TS because it gives us all the information that we're looking for. The HS diagram is also interesting. You can see, here's one interesting thing about the molar diagram. You see how for a temperature is constant, these lines flatten out. Remember how we've said for an ideal gas that enthalpy is only a function of temperature? Here it is. See how they flatten out? So for high values of enthalpy, gases are up here in the upper right-hand corner of this thing. So upper gases are up here because it's obviously very superheated, right? Superheated nitrogen and oxygen is where we are. So this is kind of showing evidence that as you get into this vapor only or superheated vapor region, the temperature is, or the enthalpy, sorry, is only a function of temperature. So that's what we're trying to say here. But anyways, that's the only thing interesting about this. All right, the last thing I want to do, and as an example, before we end class today, is to talk a little bit about using the steam table data and determining the property data for a process which there's a change in entropy. So let's see. Uh-oh. My iPad just died. Well, it didn't die, but it needs to look at me or something. Okay, so all right. So here we go. Here's the example, and let's solve it. Okay? So the process looks good like this. So what do we have known? We'll just say all right, so let's just say known. We have property information. Oh man, my handwriting is getting bad. About steam. Okay, we're supposed to find. We're supposed to locate the states on a TS diagram. Okay, so we're supposed to locate them on a TS diagram. Okay, so the next thing we're going to do then is look here at where what the TS diagram looks like. And so let's see. Well, the diagram is part of the analysis. So let's go. Just go to here. Well, we're gonna just. I don't know if we need to make assumptions, but we'll just say. We'll just say none, because we're looking just things up on a TS diagram. We're not really making assumptions about these things. We're not actually solving any problem here. All right, so then what we're going to do is we're going to now solve this thing in terms of, I'm sorry, it's not solve, but we're going to do an analysis, which includes a diagram. Diagrams. Okay, so then A is given as T1 equals 40 degrees C, and T2 in degrees C, so, oh wait, we have a process here. No change in specific entropy. Oh, we have a process. Okay. Sign states on a TDS diagram for a process. Okay. I didn't really look at the problem. Sorry. Let's see. What does it say? Determine the indicated property data for a process in which there is no change in specific entropy. Oh, so S2 equals S1. Okay. S2 equals S1. That seems like kind of an important thing to know, right? Okay. So T1 is, let's see, X1 equals 100%, P2 equals 300 kPa, and we're supposed to find T2. All right. T2. Oh, both things we're supposed to find T2. All right. Okay, so we're supposed to find T2. All right, so now let's do this. So let's see, T1... quality is 100%. So it goes like this. So we have a T and an S diagram. Now let's look here. All right, T1 equals 40 degrees C. So it's 40 degrees C. So this is 40, right? And then so it's going to do something like P2. So the entropy is going to stay the same, right? So it's got to do something here. Because P2 is equal to 300 kPa, I guarantee that 300 kPa is higher. So this is on some constant pressure line. And then this is, so we're going to have superheated stuff. Let's get rid of this. Make a better one. Okay, there we go. All right, so our TS diagram's like this. And then so this is state 1, and this is going to be some state 2. This is 300. This is some unknown. All right, so if we look this up in the tables, let's just do that quick. I'm running out of time. Let's just do that quick. Let's see if I can look at my book here. Vital source. There it is. Let's look at here. Table of contents. Let's look at tables. SI tables. Let's look in table A2. Oh, actually, no. Let's look in table... let's look in table, so A2, so we have to find, so the first thing was we're going to look in table A2, we're going to find what this pressure is. So A2, if we know at 40 degrees C, where is it? 40 degrees C is here. The pressure is, in bar, is 0.0, so it's 73 kPa, right? Let's see if I get that right. Yeah, 0.0738 bar. 0.0738 bar. Okay, and then 40 degrees C, and so S1 equals SG at 40 degrees C. which is equal to, if we look here in the table, 40 degrees, and S is this column right here. SF, oh man, yeah, SG, I'm sorry. SG is here at 40, right above my picture. 8.257. 0.257 kilojoules per kilogram. Okay. All right. Good. So we know that we have to go up, right? Yeah, so what we have to do is look up, and we have to find out where this is. So we're going to have to maybe interpolate in the table, the next table. So we don't have time for that because I'm running out of time. But let's see. So if we go to A4, let's go to table A4, and we can find out where it is. I have it. I have the answer, so at least I'll put the answer in the solutions. But A4 is saturated at 300 kPa. That's 0.3 megapascals. Do we have it? 0.3 megapascals. Here we are. Okay, so what temperature are we at? So it looks like it's 8 point, we said the entropy was 8.2, and it's S2 equals S1. S2 equals S1 equals 8.257. And so this falls here, if we look 8.257, it falls between 440 and 500. 440 and 500, right? So if we interpolate from what is it, table A5? Is this A5 or A4? We get T2 is equal to 476.2 degrees C. Okay? 476.2 degrees C. So that's how we get it. Okay, that's how you got your T2. Did I ask for the delta U? It asked for delta U as well. We can calculate delta U. So delta U, let's see, I calculated, so U2 minus U1. U2 is UF at 40 degrees C, which is equal to, if I look at here, UG at 40 degrees C, which is 2430.1 kilojoules per kilogram. And then we also know that we have to find now, interpolate. We have to interpolate to find U2 at 476.2 degrees C and 0.3 megapascals. Okay, and then so U2 is then equal to U2 is then equal to, what is it here? I have the answer here. U2 is equal to 3090.5 kilojoules per kilogram. And so delta U is equal to 3090.5 minus 2430.1, which is equal to 660.4. Okay, so I'm out of time. So what I'm going to do is I'll do the second example problem by myself and post it in the solutions. But you can see that, let's see, if I go back here, oops, I haven't been copying this down anyhow because I've been looking at the tables. So here's my solution, right? So I interpolated to find that. So sorry about that. So delta U equals U2 minus U1 here at the top. And then interpolate to find U2. And then U2 equals 3090.5, and delta U then is 660.4. Okay, so you'll have an opportunity to practice this. They'll give you something like this for your homework. But I recommend that you kind of look at my example solution, and you can solve this. So I'm going to next. I guess what I'll do on my own is I'll do a part. I'll do the part B where I have T1 and T2 here with constant entropy, and then I'll do this one and I'll post it. Okay, I'll post it before lecture tomorrow. It's Sunday. Okay. All right. Thanks, everybody. Look forward to seeing you again on Wednesday. Please, of course, let me know if you have any questions or concerns about the class and lectures. I will do an announcement about the second midterm exam. Most likely the second midterm exam is going to occur and then probably next week, not this week, but the following week. So April 16th, something like that, I think is the date. But I will make an announcement for that, and also how I intend to do that exam. I haven't figured that out exactly yet. So stay tuned. Okay? All right. Have a good day, and we'll talk to you soon.